RF Man here. Today I want to continue my discussion on how to design, build, and test an RF amplifier. In part 2, I showed how we could use LTSpice to measure the input impedance of a circuit, and I demonstrated that with a transformer using different turns ratios to match to 50 ohms. So those of you who viewed that video, we talked about the turns ratio and the impedance ratio and how that's used for transforming the input impedance to match the output impedance. Now in that demonstration, I just used a 50 ohm resistor, okay? But in later demonstrations, I'll actually show how we use LTSpice to measure the input impedance of this entire circuit. So that would include the AC coupling capacitors and the dampening resistors, and of course the impedance of the two transistors, the gate impedance. So today I just want to go through the input circuit and talk about some of the fundamentals, and then actually do some bench measurements and some demonstrations to show how this works. So the biasing I'm using is 4.2 volts. That gives me about 300 milliamps of bias, and that will vary as temperature changes, as temperature goes up and down. And for temperature compensation, I'm using 2 Zener diodes, which have a positive temperature coefficient of 8 millivolts per degrees C to compensate for changes in temperature. And the Zener diodes also, these are 12 volt Zeners, so they regulate the 24 volts down to 12 volts and then provide some temperature compensation as well. So let's go through this. Let's focus first on the input transformer. Now, an input transformer is a relatively simple device, right? We have a core and we have some windings. Well, for RF, it's a lot more complex than that. And what I'm showing here is the equivalent model of an RF transformer. So of course we have our primary winding and secondary winding, okay? And these are the phase dots, so it shows that the input and output are in phase. And all of these other effects are considered parasitics. So what do we have? On the input side, we have the winding resistance, that would be the resistance of the wire. We have the capacitance of the primary winding, okay, so the capacitance between each winding. Then we have our leakage inductance here and our magnetic inductance, and then we've got some core losses as well. There's some core losses. Now all of these are distributed, okay, but what we do to show an equivalent circuit is we show the effects as lump components, but actually all these effects are distributed effects. So we have distributed inductance, distributed resistance, distributed capacitance, etc. Now on the output side, we also have the capacitance between the windings, we have leakage inductance, and we have the winding resistance. And then finally, we have the interwinding capacitance, which is the capacitance between the primary and secondary. So what's the point of all this? The point is, a transformer is not as simple as it looks, okay? There's a lot of other parasitic effects in the transformer, and they have to be considered depending on the frequency that you're operating. So honestly, for high frequency, the main concern would be the leakage inductance on the input and the output, okay? And that's what I'm showing here. So this transformer has a turns ratio of 1:1. So I have 2 windings in the primary, 2 windings in the secondary. That's 11.2 microhenries for the inductance for each side, okay? And we take the turns ratio and we square it, gives us the impedance ratio. But in this case, our turns ratio is 1:1, right? 2 divided by 2 is 1. So we have a 1:1 turns ratio, 2 turns on the primary, 2 turns on the secondary. That's 1:1, okay? And then the impedance ratio is the turns ratio squared, but 1 squared is equal to 1. So the impedance ratio in this case is also 1. Okay, and the way we measure the leakage inductance is we measure the primary side with the secondary side open, and then we measure the primary side and short the secondary side, and we will see a difference. Okay, and that shows us how well the transformer is coupled. Now, no transformer has a coupling coefficient of 1. Okay, it's more like 99.99% or 98%, or in this case, this one's 0.9985, 99.85%. So depending on the construction of the transformer, you're going to have more leakage or less leakage, also depending on the turns ratio. So then on the secondary side, we measure the secondary while the primary is open, and then we measure and short the primary and measure the resulting inductance. So when I do that, the difference is 33 nanohenries on the primary side, which is the source side, and 33 nanohenries on the secondary side, which is the load side. So leakage inductance is relatively low, could almost be ignored in this case. I did not do any compensation across the transformer because the leakage inductance was fairly low. I also modeled that in LTSpice and didn't really see much benefit trying to compensate for the leakage inductance on the output. So that's how it's measured. We do an open and short test on the primary, secondary side, and we take the difference. Okay, so let's move on. Now, I'm going to go and show this in part 4, but I used LTSpice to measure the input impedance of our circuit. And as you can see here, I measured it at 20 megahertz. Here was my real part. Here's my imaginary part. Remember, we take the square root of the sum of the squares. So here's R squared. Here's, in this case, you see minus J. Okay, so it's capacitance. Okay, and we take that and we square it. Then we add the two together and we take the square root. So I measured 49.3 ohms. So the closest ratio to 49.3 ohms is going to be 1-to-1, right? So if we look at this calculation, here's our input impedance of the circuit. Now, with that said, the input impedance of the circuit consists not only of the transistors, but also the coupling capacitors and the two 3.3 ohm dampening resistors. So we're measuring the input impedance of the entire circuit, and that's what we need to do to have a proper match. So if we take the ratio, right, okay, it's 50, which is the input, right, from our transceiver, and the measured input impedance is 49.3 ohms. You can see the ratio is 1.02, so the closest ratio is going to be 1-to-1. Okay, and if we take the closest turns ratio and we take the square root, we get 1-to-1 as well. So remember, here we're measuring the impedance ratio, and here we're measuring the turns ratio, right? So in this case, it's the same, but the turns ratio squared equals the impedance ratio, and the square root of the impedance ratio equals the turns ratio. So it's pretty straightforward. So here you can see this is what I decided to use: 2 turns on the primary, 2 turns on the secondary. It's a 1-to-1 ratio, and there's the measured inductance here. I'm also showing how to calculate the minimum inductance of the transformer. Okay, this is, I think, more critical when we're using transformers that are constructed with copper tubing and end plates. But here, when we're using windings in the primary and secondary, we're not too concerned about the minimum inductance. But that's how you calculate it. It's R, which is 50, divided by 2 times pi times frequency. Excuse me. And you can see the minimum inductance for the primary side of this transformer should be 2.2 microhenries. But again, in this kind of construction where we have a primary and secondary winding, we're not really concerned. The other type of RF transformers that we're all familiar with would use brass tubing and end plates for the primary or secondary side. And there, yeah, it's a little more critical that you meet the minimum inductance requirements. So let me go back to this side of the slide. Okay, so here we are, 20 megahertz. Okay, I got a 1-to-1 SWR calculated from my simulation. And then we had four other places here. I used 10, 15, 20, actually 25 on my spreadsheet, and 30. And you can see we got fairly good SWRs across the frequency band. Remember, I'm tuning this amplifier from 10 to 30 megahertz with a 20 megahertz bandwidth. I am doing that intentionally because I'm using this as a prototype for another design. But still, we have 20 megahertz of bandwidth. You can tune it also on the lower side as well, and you can use LTSpice to measure what the input impedance would be at lower frequencies. So that we'll go through in part 4. So that's basically how we determine the input impedance ratio. Okay, also what you'll see in the circuit is we're using series gate resistance for stabilization. Okay, so let's talk a little bit about that. All right, so let me just review that one more time. We said that the Q equals the reactance divided by the resistance. So as we increase the resistance, we're going to lower the Q, right? And lower Q values produce less energy in the circuit and reduce the resonant ringing or the tendency for a circuit to oscillate, okay? And that we see here. Here's a higher Q, there's our lower Q, and we see that there's less energy, but also there's a greater bandwidth. So it does help on the bandwidth too. And here's the formula for bandwidth, okay? It equals the center frequency divided by the Q. So in this case, we want to have a higher bandwidth, so we have a fairly flat response across the frequency range, and I will go ahead and demonstrate that with the NVA. So here we're using series resistance for stabilization, 3.3 ohms, okay? The best thing to do here, if you're using LTSpice, you can model this by using a different resistance value. The general rule is somewhere between 1 and 10 ohms. Of course, this will affect your drive level as well, so you have to look at all your design requirements to determine what the appropriate resistance value should be used to stabilize the circuit and dampen oscillation. Of course, you can use feedback as well, and you can use what's called a shunt gate resistor from the gate down to ground. So that's our stabilization in the circuit. Now I want to go ahead and focus more on the circuit itself. Okay, so just bear with me here while I adjust my camera. I'm going to try to get everything in clear view if I can. Okay, so here we have the board set up. I'm measuring the SWRs on the input with the nano VNA, and we're going to demonstrate how we set the bias and how the bias affects the drain current. So I'm running the circuit at 24 volts, could go up to 28 volts, but I'm running it at 24 volts. Okay, and here is the drain current, which I said will vary with temperature. So when I first powered this up, it was about 300. Now it's about 350 milliamps. Okay, and we're going to go ahead and do a few things here. First, we'll go ahead and measure the bias voltage. So you can see that here our bias voltage for Q1 is 4.23. Okay, and we can measure the bias voltage for Q2, and it's 4.0. 0.24. So they're within 10 millivolts or so. Okay, now if I want to adjust that, I've got these two potentiometers here. Okay, this is for Q1, this is for Q2. These are multi-turn pots. Best to use multi-turn potentiometers for measuring and adjusting the bias voltage, so you have a little bit more control over the voltage level and a little bit more accuracy. So that's what I recommend. And this circuit, we have basically a voltage divider. So we have a 1K resistor and a 10K potentiometer. This makes up a voltage divider. Then here's my Zener diode that I use to regulate 24 volts down to 12 volts and provide temperature compensation. And then this is just a small RF choke that drives the gate of the transistor through the dampening resistor here. So let's go ahead and, while we measure the voltage, adjust the bias voltages. And what would you expect to see? Okay, so I'll refer you to the current measurements here. Okay, as we turn up the biasing, we obviously will increase the drain current, and that's what you see there, real time. Okay, so I like to set it at the quiescent point, which is about 150 milliamps for each of these components. And if you set it higher than that, you'll basically reduce the efficiency of the design, and the transistors will start to heat up quite a bit. Okay, so we're going to go ahead and adjust this back down. Okay, and we'll go ahead and do the same here. We'll just bring this down to 300. Now again, this might drift a little bit as the temperature increases and decreases. I'm not using a fan right now to cool off the heatsink, so there'll be some temperature rise on the devices. So you might see some fluctuation as we go on here. But so each device is 4.2 volts. That's the threshold for the IRF510. And we'll be taking a closer look at the data sheet in the next part. But that's the bias current. So 4.2 volts is right at the threshold. The transistor just starts to conduct, and we've got about 150 milliamps on each device. Okay, so you can clearly see that MOSFETs are voltage devices, not current devices like a bipolar transistor. So it's very easy to bias these with a simple voltage divider. And as we increase the gate voltage above the threshold in the specification, we start to see that the drain current increases. That's the current from the 24-volt power supply that's flowing through the drain to source, or drain to ground. So we demonstrated that to see how it affects, how sensitive it is, and why we use multi-turn pot. You can see that it is a pretty sensitive adjustment for MOSFETs. So now I'm showing here the SWRs from 10 megahertz to 50 megahertz, and you can see it's fairly flat. It ranges from about 1.6 to 1.2 depending on the frequency, and you can see it's better on the high side than it is on the low side. And we talked about why we add this resistor across the output of the transformer, right? We're calling this a Q dampening resistor, right? So again, it's the ratio of the impedance of the transformer and the resistance, right? So if we basically increase or decrease the Q with this resistance value, right? And what we want to do here is reduce the Q to increase the bandwidth. So what will happen if we go ahead and lift that resistor? Just give you a quick demonstration here on what the results would be. So I will go ahead and raise this resistor off the board here. Okay. And what do we see? We see immediately that we have less bandwidth on the low end. And we see the SWRs went from about 1.6 to 3.8. So we've got a significant rise in the SWRs on the low end. So if we add the resistor, and I can do that real time just by go ahead and holding that in place. If we add the resistor, right, we reduce the Q, increase the bandwidth, and you see we have a much better SWR on the low end of the band. So that's what that resistor is used for, to help us increase the performance of the circuit by increasing the bandwidth and reducing the SWRs. Particularly, you see it affects primarily the low end. Okay, let me go ahead and solder that back into place. Okay, so that's acceptable performance with the SWRs across the band. And I'm not using any other tuning. I could place a tuning capacitor across the transformer, typically a trimmer capacitor, but I'm satisfied with that. That looks good to me. That looks fine. So that's the demonstration for today. We talked about the input circuit, and we talked about the biasing circuit being nothing more than a simple voltage divider. We talked about using the Zener diodes for regulating the supply voltage and for temperature compensation, and the use of these chokes, which just choke out the RF so it doesn't feed back into the 24-volt power supply. And then we talked about the dampening resistor across the transformer, and also the dampening resistors used to drive each of the gates to help us stabilize the circuit. So that's the demonstration for today. We'll continue with part 4, RF Man.